Oh, maybe it is recording, huh?
Yeah, it's recording.
Oh, it's recording.
I can restart it.
Okay, no, that's okay. I mean, it's natural. I mean, so, okay. So, yeah, so the two topics that we want to cover in this course is Dirichlet's theorem. So, infinite primes in arithmetic progressions. And the topic 2 would be modular forms. Okay, so let's look at Dirichlet's theorem. So this is a theorem that was proved by Dirichlet in 1837 in a very famous paper. So, sorry, I can state it like this. Let A and B bigger than or equal to 1 be integers. A and B equal to 1. So it means that they are relatively prime to each other. So we have two integers bigger than or equal to 1 that are relatively prime to each other. So then the theorem says that there exists infinitely many primes in the arithmetic progression A plus NB n equal to 0, 1, 2, so on. So in other words, the progression is this arithmetic progression, starts with constant term A, then moves by B units each time, A plus 2B, A plus 3B, so on. So now what does it say? Of course, if A and B are not relatively prime, then this term A plus NB is never prime because there's a common divisor between A and B, right? So this is at least a necessary condition for having a chance of having primes in the sequence, any primes in the sequence at all. But the question is if there are finitely many primes or infinitely many primes. That's the question. So this theorem, that's the statement of the theorem. So this theorem should remind you of something. And perhaps it reminds you of something special case of this, which would be Euclid's theorem. Euclid proved around 300 BC that there are infinite primes. So let me write as a special case. So this was Euclid, roughly 300 BC. In fact, it appears in his famous book, Elements, or Elements of Geometry, or whatever. In the book, so this book of Euclid is interesting. It has, I believe, 13 chapters or 11 chapters, books, huh? 13? Okay, yeah. And at least one book is devoted to number theory. Maybe more than one book is devoted to number theory. And in that book, which is part of Elements, one of the great theorems he proves is the following. So this is the case of A equal to B equal to 1. Euclid said that there exists infinitely many primes. There exist infinitely many primes in the sequence of natural numbers, right? 1, 2, 3, 4. Right? So that's what Euclid proved. And let me recall proof of Euclid for you, just to give a kind of point of reference so that we'll see how different methods are going to be. So the way, this is a classic result, of course, the way Euclid proved it, the proof was by contradiction, right? So by contradiction, so he said that assume there are finitely many primes. Assume there exist finitely many primes only. So let's call them P1, P2, Pn. Just there are n of them. All other numbers are products of these things. Then let's consider the number. I don't know, A equal to P1, P2, Pn plus 1. You just multiply them and you just add 1 to it, right? Now, what's the nature of this number? Well, this number is bigger than all these things, P1, P2, Pn, right? A is bigger than Pi for all I, right? So this is not a prime, okay? So it has to be divisible by primes. But what are the primes that has a chance to divide this? Only among P1, P2, Pns. But you can see that because we have added 1 to it, cannot divide these things, right? So A is not a prime. And Pi does not divide A. So this is a contradiction. So this is what Euclid was able to prove. And this situation basically stayed as is for almost 2,000 years. So the amount of knowledge did not increase in this regard regarding primes for 2,000 years. It was same level of understanding of prime. Then Euler entered the scene. So Euler, so the next episode really. So this is where Euler entered the scene. So Euler wrote this famous paper around 1737. Euler also proved that there are infinitely many primes, but proved much more. So let me tell you how Euler proved this. Euler reproved Euclid, its theorem, with a totally new technique. And this new technique, as I will show you, actually gives you much more than what you can gain by this classic method of Euclid. So now here's perhaps the biggest idea in analytic number theory, which is the introduction of zeta functions, okay? So define zeta function. This was introduced by Euclid, by Euler, I'm sorry, in 1737. I'm not sure what notation he used. I'm pretty sure the notation zeta is due to Riemann. Maybe Euler used a different notation. I most probably used a different notation, but I don't know what notation he used to denote this. So, but universally we denote it by zeta of s, which is equal to 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, which we can just write sum 1 over n to the s, and from 1 to infinity, right? That's the zeta function of Euler. Now, what S is doing over there. For Euler, S was a real number only. And in fact, Euler just thought of S as an integer bigger than 1. That's all he looked at. So the range of S for Euler was real. Or in fact, most probably it was just integer that he really focused on. But that's okay. But S bigger than 1 real. So this is 0, this is 1, and this is the range of S. Now, so this is an analytic object. It's a special type of series. Now, one thing is to worry about convergence of the series. And for the convergence of the series, you can see that this is convergent in view of something called, in calculus, you call it t-test or something, because t is equal to s and is bigger than 1, so this is convergent. So, so note that zeta of s is convergent for any s bigger than 1. For now, it's just real, but that's okay. Okay, so we have this object. Euler introduced this object, and he had some other reasons to introduce this object, but this was sort of several ideas, several problems came together at the same time for him and led him to great discoveries. So this is the first idea, zeta function. It's really maybe the most important idea in analytic number theory is to introduce this sort of objects, zeta functions. Now, the second thing that Euler observed about the zeta function is something called the Euler product formula. So let me write it. Any questions, by the way, so far? Everything okay? No questions? Okay, good. So now the second point is, yeah, sure.
At that time, when you knew something about complex numbers.
Yes, they knew already something about complex numbers, like about already complex numbers were introduced in 1600s. So it was like more than 200 years, but they had very funny ideas. Well, we say funny now, but it was a big challenge for them to grasp complex numbers. We think we understand them. I hope we are right, but these guys didn't think that the complex numbers was shrouded in mystery, in total mystery for them. There are some objects in current mathematics that are like that for us. And you have to go and find those objects that are mysterious. But for them, complex numbers was the biggest mystery. But they still worked with it. They still worked with it. They made mistakes. I mean, they were worrying about what is I to the power I, for example. And yeah, lots of things. If log of -1 is defined or not, what is log of I? And they were doing all these calculations, but by try and error. But there wasn't a solid foundation for complex numbers, but they existed.
So it was too much to expect from Euler to this function as a complex.
Absolutely, yeah. So as a holomorphic function, as we'll study this, it was way beyond Euler's reach, definitely. Even the idea of holomorphic functions, in some sense, it was introduced much later, but in some sense by D'Alembert, which was more or less same time as Euler lived in France. Euler worked in St. Petersburg, Germany, most of his career. So, but that's okay. I mean, we don't need right now to consider S to be a complex number, but this becomes the real issue soon. But what Euler proved is the following thing, Euler product formula. So that's the second, as I said, biggest idea in all of analytic number theory, because we are going to see this Euler product formula in many, many different guises again and again and again in many, many areas of in analytic number theory appears, and also in algebraic geometry. So what is it? It's the result that sum 1 over m to the s and from 1 to infinity is equal to product of 1 minus 1 over p to the s, the minus 1 over p. So this right-hand side, p belongs to primes. So a sum over all integers is related to a sum, to a product of over all primes of these factors. Now, this factor is so important. It's called Euler factor. It's a very important mathematical gadget, maybe with power minus 1. You can call it Euler factor. So the product of Euler factors over all primes is related to zeta function, which is a sum over all integers. So this is zeta of s. And this result is true for all s bigger than 1 at least. Okay. So this result, the proof of this follows from the fact that any integer can be uniquely decomposed into products of primes. So proof, I mean, if you don't want to be too careful about analysis and allow yourself some manipulations without necessarily worrying about analytic details, it really boils down to the following. Proof boils down to, I will sketch the proof soon, but boils down to unique prime factorization. So this is unique prime factorization for all n belonging to n. So this is the set of 1, 2. For me, set of integers excludes 0, so it's just 1, 2, 3. Now, what does this mean? It means that we can write any n as product of pi to the power ni over I. The pi's are primes. And this product is essentially unique up to some trivial rotation or permutation of this prime. So if you use this, then you can use. So now there is something here which is interesting. That's 1 over 1 minus x. This geometric series is very important. So this is equal to 1 plus x plus x2 plus x3. Okay. So then using this, you can write the right-hand side as sum 1 over p to the power ns. N is a bad idea. I just put ks here, right? K from 0 up to infinity, right? You can just do that. And then you replace on the right-hand side each factor, each Euler factor by an infinite sum. You take products of infinite sums. So let's see what happens. Then from here, we get that product of 1 minus 1 over p to the s minus 1 over all primes is equal to product of over primes of sums of 1 over p to the ks, right? K from 0 up to infinity. Are you okay with this? Good. Then we can write down, so this is products of sums. It turns into sums of products. Now, we can just write it as sums of products. So we can just write it as sums of products of things like this: 1 over P1 and 1 over P2 and 2, 1 over Pk and k, for example, for all k, and then such that n1 plus n2 plus nk is equal to n. Now, so this is this summation is over all k and n. Now, I missed an s because there is a factor of s here. Okay, now if you use this, you can replace this factor in the denominator by n, and then n to the s. So this becomes equal to sum 1 over n to the s. So what I did, I reordered this infinite product. I wrote it as sums of products, but these products at each time you just get finite number of terms, and when you multiply, you just collect terms that add up to n, and you get this one. Yeah. Yeah, we will get all the n's exactly because I mean here we have if you have an n, it's just you just write it like this, right? P1 n1 P2 n2 Pn, and then you just pick those right factors from denominators here. So we do get all the n's, and by this. Okay, so now this is something that it's a sketch of a proof. It's not a complete proof, because in the proof you have to worry about convergence of these things and changing multiplication and summation order of these operations, but these are all okay. But it still is a good idea. You just try this quietly yourself. I think there's an assignment that asks you to do this sort of manipulations. Maybe something simpler. I'm not sure. Okay, but this is what Euler used. So let's just go to that. Any other questions or comments before I tell you how now this can be used to show that, first of all, there are infinite number of primes, and second of all, you get something that was new after 2,000 years. Some progress was made as a result by introducing this idea. No questions? Okay, good. So now let's see what was. So this was the kind of warm up for Euler's idea, then Euler's proof. So then Euler proved that so this is Euler's proof of infinite primes, or infinitude of primes. So the proof goes like this. Again, it's by contradiction. Assume there are finite number of primes. Assume there exist only finitely many primes. So, I mean, I don't have even to name them. So P1, P2, Pn. Then in the Euler product formula, the right-hand side is a finite product of those Euler factors, right? Then right-hand side of Euler product formula is equal to product of 1 minus 1 over Pi to the s minus 1 I from 1 to n, right? Finite number. Now, let's see what happens to the thing as s goes to 1. So now, sigma 1 over n to the s, and from 1 to infinity approaches to what as s goes to 1, you think? You see, S is a real number bigger than 1, and the value of the function is defined for all in that range. And we are worrying about the limit of this quantity, this zeta, as S goes to 1. So what is that limit? Sorry? It's infinite, yes. This is infinite because, in fact, this approaches to sum 1 over n, which is the harmonic series, right? This is the harmonic series. And this is what you learn in calculus that, so this is infinite. Okay, but the two sides are equal, so the right-hand side also should approach to infinite. But it doesn't if there are only number of primes. Okay, so, but right-hand side does not approach to infinite as S goes to 1, since there are just finite number of primes. In fact, it approaches to product of 1 over 1 minus pi inverse I from 1 to n, and this is different from infinity, right? This is different from infinity. Okay, so this is the end of the proof. So Euler, by this method, was able to show that there are infinite number of primes. So you may say, okay, well, compared to Euclid's proof, this is much, much more complicated. It's like using a rocket to go from here to, I don't know, Waterloo or home or something. You just need a bicycle to get home, not a, you know, multi-billion-dollar rocket go there. And this was like that. I mean, the tools that he introduced are amazing, but the point is that he didn't stop here. He proved something that was new after 2,000 years. Now, let me tell you what was new. So what Euler proved, okay, what Euler used is product formula to get something new about primes. In fact, he proved the following theorem in the same paper, which is Euler 1737. He proved that the sums of reciprocals of primes is infinite. So not only there are infinite primes, but they grow in a certain way. They are not just like any other sequence. So they are like, they are such that their reciprocals add up to infinity. It's not finite. That's the important thing. There is sums of the reciprocals is not finite. What does it say? So I will give a proof, but let's think about what does it say. So what does this really mean? So this means that, so okay, do you have an idea? Do you want to think about maybe? I invite you to think about what really this means in terms of distribution of primes, in terms of density of prime, in terms of how many primes are out there. Well, we got some interesting information already by Euclid that there are infinite number of primes. That's good. But this is something saying something much more, I'm claiming. What does it say? Yes.
Summation similar to 1 over n.
Yeah.
N. There'll be some time that doesn't.
Yeah. Yeah, exactly. That's the right intuition. It just says that there are many primes, actually. You see, the set of primes is not very thin. If it was a thin set, like n squared, for example, you see, N squared, I consider a thin set. You see, they jump so fast, like squarely, so that if you do the reciprocal summation, you would get finite number. It's the thinness of the thing. But this is not very thin. The set of primes is like almost like 1 over n. Is a thick set. There are many, many primes. So it means, so let me just, okay. These are all ideas, okay? I'm not making it precise. So we have to develop some intuition about what we're going, and then we will have some quantitative measures. In what sense we're saying this set is thin, in what sense this set of not thin, and things like that. But compared to set of squares, well, this is another set of numbers, right? N squared, n equal to 1 to infinity. Well, for this one, sum 1 over n squared is less than infinite. So this set is, we call it, it's a thin set. In fact, if you take anything like n to the alpha, it's still a thin set, right? But this is not like that. This is behaves like, I mean, now I say behaves like this is wrong, but I just say it as an, I put into 3 quotation marks. This is really has to be understood in a very, very qualitative way. Behaves like sum over the harmonic series, which is again infinite. Well, this doesn't behave like that if you want to be very precise, but at least in the sense that both sum to infinity. So it means that there are many. So basically, this now I want to give you a sense of what it means. This really means that there are many primes. Not only there are infinite number of primes, but there are many primes. So there exist many primes. Many means is a local statistics, means that around any number there must be some prime in some sense. I will try to make it more precise. There are many primes. Okay, so this is the theorem of Euler. Let me give you the proof now. Using the Euler product formula again. Any questions? Okay, so let's see how the proof comes about for this. So let's see. I mean, proof. So we have sum 1 over n to the s is equal to this product, Euler product, over P. Now, again, I use the same geometric series to write it as product of infinite sums. Okay, so this is, I just write it as product of sum 1 over P to the ks over P and k from 0 up to infinity. Now, if you look at that, you can just see that these terms always start with 1, you see? So this is like product over P, 1 plus, the next term is 1 over P, and the next term, is 1 over P to the S. And then the next term is 1 plus P to the 2S, 1 plus P to the 3S, so on, right? So when you multiply these things, you can always start with 1. You just pick the first term, just 1. It's just like multiplying in algebra, 1. And then you just multiply these things, which is sum 1 over P to the S over P plus sum 1 over P to the 2S over P plus sum 1 over p to the 3s over p, and so on. Right? Is that okay? We are expanding infinite products of infinite sums of infinite terms. So you can just write it like this, in this order. And this is okay. Okay, so now I'm out of maybe my limit, hopefully not. So this is true for s bigger than 1. Okay. So now, yeah. So what I want to say. Now, look at that. Look at this term. Now, notice that sum 1 over p to the 2s over p is convergent. I mean, yeah, we have that convergent by the p-test, because this starts with the squares. I mean, it's bigger than 1. Yeah, so this is convergent. I mean, we are all in the range s bigger than 1. Sum over 1 over p to the 3s over p is also infinity. Sorry, less than infinity. And the point is that the sum of all these things also is less than infinite. As s goes to 1. So basically, you can write this relation in the following form. Sum 1 over n to the s, right? And from 1 to infinity is equal to 1 plus sum 1 over p to the s over p plus, let's call it r of s. That's the remainder that corresponds to all these terms that I have left out. Okay, so this is r of s. Now, this formula is correct for s bigger than 1. And what I said here is that this r of s has a finite limit as s goes to 1. So this is finite. This is a one of your assignment questions. Maybe the first assignment I just posted, maybe it's there. That's just very easy because you have to estimate these sums of just use integral test to estimate each term and then estimate the sum. That's not difficult. All right. So then what is it? So now let's take limit. As s goes to 1. Well, the left-hand side goes to infinity, right? You know that. Okay, left-hand side goes to infinite implies that the right-hand side must go to infinite. But this is finite, okay? As s goes to 1, this doesn't blow up. So this sum 1 over p has to blow up because, well, we know that the sum of these 3 terms has to be infinite. 1 is finite, this is finite, so this has to be infinite. Okay, so that's what that's the idea. Okay. Okay. So sum. So that's the information that we have about prime so far using. So Euler already knew that there are as many primes such that there are so many primes such that the sum of the reciprocals is not finite. So they don't grow too fast. In other words, I mean, each interval there must be many primes in each finite interval of integers. So this was really new deep information inside that Euler obtained only through analytic methods. Using elementary methods to prove any of these statements takes a lot of work, and I'm not sure even if many of them can be proved using analytic techniques, using non-analytic techniques, as for example Euclid's techniques. Yes. Yes.
Are there any
Yes, for this sort of things, the sum at s equal to 2 is very important, as you know. That's the famous Basel problem. And Euler, I think, wrote first a paper on that. And that's how he was led to these sums of reciprocals of and like 1 over n to the s, I believe. And then how he discovered the Euler product formula, I don't know. I think people have historians of science have investigated this, and they have some ideas how he came across. But this is such a deep idea, this Euler product formula. But yes, and for other integers, the summing of these things is important. Yeah. But in terms of distribution of primes, s equal to 1 is a very, very particular point. It's because that's the point where the Riemann zeta function has a simple pole. That's the only point. So that's very, very important. Yeah, but okay, sorry. It was a qualitative answer, not very precise answer. Any other questions? Yes. Yeah, so the question is, for example, the density of primes. How many primes are in this interval? So I will. What I'm going to say now will give you some ideas. So because I'm now discussing this paper of Euler, maybe I should also tell you what he wrote at the end of his paper. So this is at the end of his 1737 famous paper, which he did all these things, Euler writes, now that's quite interesting, sum 1 over p is equal to log infinity. That's how he ends the paper. And he claims that he has a proof of this. He gives some ideas, sketchy ideas about how this is perhaps correct. He had no doubt about it, that it is correct. We don't accept his proof. All his proofs so far are okay, but this one, we don't accept it as correct. And then now the question is, first of all, what it means. This is equal to log infinity. Of course, you can say, well, log infinity is also infinite. So this is also infinite. He has proof. So no information here. No, that's not what you mean. And log infinity, or you could put log infinity, or any strange function of infinite which would give infinite. That's not what he means. He has something. So one possible interpretation is, so in other words, if you want to interpret it correctly, you can say that sum, perhaps 1 over p, all primes less than or equal to n, just summing all primes in the interval 1 to n, reciprocals, is asymptotically like log n. Now, what do I mean by this? This is a very important notation. From analysis, perhaps you have seen, but let me introduce. F of n, we say, is asymptotic to g of n if limit of f of n over g of n as n goes to infinity is equal to 1. That's something from calculus also. So basically, it means that this quantity, this number and that number are same order of magnitude, same type of largeness they enjoy. Of course, you see, log n is not asymptotic to log n, right? You know that. You can prove it. That's much smaller. And in fact, limit of this over that goes to infinity. That limit is. They are not same order of magnitude. Like x2 and x3 are not same order of magnitude, or exponentials different. So Yeah, so, but this is, so now this can be made precise in this sense, but then this is true. This is a theorem that was proved much later. So for the proof, you can just check the Hardy and Wright book. There's a proof there. I don't know who proved it first. I'm not sure this is Hardy and Wright's proof, but it appears in their classic book. It's called Number Theory or something. There's a very, very famous classic book, Hardy and Wright. So they give a proof of this. Okay, so Euler, whatever his methods were, he had some maybe divine connection, I don't know. He had some inspirations. He had amazing calculational powers for sure. He could compute numbers, and he had tables, and he used many different methods to come across results. But he was almost always right. No matter he had a correct proof or modern, up-to-date standards correct proof or not, he was almost always right. So, and this is, in this sense, this is correct. And perhaps that's what he meant. But then, your question, yes. Yeah, so you have to go through the proof to see why it is not accepted. I'm just quoting some standard understanding or reading of that paper from other sources and I believe those sources that I'm quoting from. So I believe that they have read Euler's proof with detail and they know that it is not correct. Well, this statement is not correct, but his proof is not correct. The statement, and actually he doesn't give this interpretation. This is the interpretation that's given to the statement, and in this sense is correct. Yeah, so actually I tried to find an English translation of the paper. It's not posted anywhere. The paper is in Latin, and well, Euler wrote just in Latin, nothing else. He just wrote all his, I don't know, 1,500 papers that he wrote in his life, and many books, they're all in Latin. It's just, this was the lingua franca for the time. Anyhow, so let me now tell you, so this is a star. So you should compare a star with something that you can prove. And in fact, I give you, there's an assignment in this assignment 1. There's a question to do that. So compare a star with some 1 over k less than equal to n, the harmonic series. Do you know how the harmonic sums grow? You know that the sum is infinite. Okay, that's good knowledge, but we want to know more how it goes to infinite. Huh? Factorial. Okay. Okay, any other guess? Ln n, yeah. This grows like ln n as n goes to infinity. And you can prove this. This is one of your assignment questions, assignment 1, one of the questions. It's a good idea to try to prove this. That's not, it's completely calculus. You don't need anything more than calculus, calculus 1000, just to prove it. But anyhow, so that's, oh, ln n, sorry. So ln n, and this is ln n. So yeah, there are less primes than integers, of course. The primes they have no chance of competing with all integers. There are much less primes than integers, but the relation is like that. But now let me just do a little bit of experiment. Yes.
some on of
Yeah. Yeah. Because yeah, the relation of being asymptotically equivalent is transitive, so you can use that to conclude that. Yeah. Right. Yeah. So now let me do a little bit of maybe sorcery here to give some information about primes that's actually again becomes quite important and deep just from this observation of Euler. So let's introduce a function. Let pi of x. This was the introduction. This is the function that was introduced by Riemann, but the notation is due to Riemann, but people from ages ago were interested in this number. Let pi of x be the number of primes less than or equal to x. Okay? Number of p less than or equal to x. Sorry? Oh, small pi or big pi? Oh, this is a small pi. And I'm not sure actually it's written as number pi even. So is a pi like the letter pi? Yeah. Because that pi, I don't know, it's just somehow, I don't know. My calligraphics fonts knowledge is very limited, especially English and Western fonts. So anyhow, so let there be a number of primes less than or equal to x. So this is called the prime counting function. That's a very important function. So let's assume that this is a smooth function. If you want, you take its derivative, then pi prime of x dx is the density of primes. It basically tells you how many primes exist near x, right? Just try to be imaginative. Don't try to be hard, okay? You can be hard and say this is all nonsense. I agree, but it's also very sensible, and it even takes more courage and imagination to agree that this is good. Okay, so just be on my side. Then pi prime is equal to density of primes. Okay, now then we can write a star as follows. Okay, so this sum 1 over p less than or equal to n, we can write it as integral 1 over x pi prime of x dx. So maybe I just say 1 over t pi prime of t dt. T goes from, I don't know, 2 to x to n. Because, I mean, remember, imagine you have something like still just integration, that you have some density function, right? And this density, and you just, if there is no prime at t, then this is 0, so you're not summing, but then you're summing exactly around those points, there are primes, and how many primes are around those points exactly is 1 over p times that. So this is more or less, I mean, probabilistically, or I don't know in what sense, this is okay. This is kind of, maybe that's how Euler actually was seeing these things. Anyhow, so but I'm going to replace p by x even now. So this is x. But now we are told that this is equal to log x. So we can differentiate on both sides, okay? So what do we get? Well, the left-hand side by the fundamental theorem of calculus, whatever, is pi of x over x, right? On the pi prime of x. You get that pi prime of x over x. Well, what is the derivative of log x? The derivative of log x is log u is u prime over u, right? So it's 1 over x log x, right? Right? That's the derivative on the right-hand side. So I'm just writing asymptotically the same, but at one stage, I'm going to say they are the same. Oh, they are not the same. They are asymptotically the same. Sorry. So, and then you can simplify that. So you get that pi prime of x is same as 1 over log x. So the density of primes is like 1 over log x. So how many primes are there near number x? 1 over log x. That's the density. In a small interval delta x, there are this many. Now, I can integrate this and to get an idea about what is pi of x. Okay? So let's get that. So pi of x, which I just write integral from 2 to x, pi prime of t, dt, this is integral from 2 to x. We have got dt over log t. I mean, I should say is, so i.e. pi of x dt over log t. This function is very important. It's called Li of x. That's the Lie function, Li of x. Okay? So pi of x is asymptotically given by Li of x. Okay? These sort of heuristic hodgepodge arguments that we are doing, I mean, sort of approximate just intuitionistic ideas that we are developing, leads us to this kind of idea. Pi of x is asymptotically given by Li. And this is a correct theorem. This is called prime number theorem. So prime number theorem. So this was proved for the first time around 1898 by two people, by Hadamard and de la Vallée-Poussin, after developing a lot of complex analysis and techniques, starting from Riemann's work and all these things. In fact, it says that, yes, pi of x is asymptotically equal to Lie of x as x goes to infinity. Now, you might have seen a prime number theorem in a different way, perhaps. Have you seen in other form the prime number theorem? Had you seen prime number theorem before? In what form?
Density.
Oh, density is 1 over log x, yes, okay. But then what about pi of x itself? There's another formula for pi of x. It's x over log x. So this is, let me write it alternatively. Pi of x is x over log x. Because honestly, computing the integral is a kind of hurdle on the way, right? Understanding. But here we're saying that pi of x is x over log x. Now, this is also correct because this function, x over log x, is itself asymptotic to Lie x. And this is one of the assignments that I was assigned in assignment 1 for you to do. So pi of x, I mean, not pi of x, but x over log x is asymptotic to Lie of x. Again, this is elementary, this is calculus. But you should try and sit down and prove it. That's a useful exercise to do this. So you might say, okay, so this is it. I mean, which one is correct? Well, both are correct because in asymptotics, there's not a unique formula, right? Some quantity can be asymptotic to x2, and then can be asymptotic to x2 plus x, can be asymptotic to x2 plus x plus log x, x2 plus x plus log x plus 1 over x, and so on. All those extra terms are become relevant at one stage. And in this case, this is a much better approximation than x over log x. Already Gauss and Lejeune knew this because they compiled tables of prime numbers, and they noticed that they go very well with this rather than with this. But this is asymptotically also is correct. Okay, so already from Euler's observations of 1737, you could guess that the form of prime number theorem would be of this form. And so that's really huge advance he made using these techniques. The introduction of zeta function. And what was the second idea that Euler used? Euler product formula, yeah. Introduction of Euler product formula. The two things, no one is good without the other. You need both. You're relating integers to primes through that magic formula. It's like a magic formula. It's like a black box, and you just. So now this was a bit of the yes. No, that's fine. It's not a sparse. Yeah, exactly. That's the right way to put it. Yeah.
And how
so if I understood your question correctly, you want to know about the meaning of this this thing, this thing, for example. Yeah, there are many primes. Yeah, in what sense there are many primes? Yeah. Yeah, for example, now we know that it is not true that the nth prime is bigger than or equal to n squared for large n. The nth prime cannot be bigger than or equal to n squared for large n. Because if that was the case, then sums of reciprocals would be finite. And it's not true that the nth prime for large n is bigger than or equal to n to the power alpha, even for alpha bigger than 1. So you get some bounds in the sense that at least this sort of statements are correct, that it's not true that for large n's this nth prime is bigger than or equal to something. It's not true. It's smaller. It means that in that interval there must be primes. So yeah, at least in this case, we are comparing with another series which is convergent, and this one is divergent. So we know that the thing cannot be bigger than or equal to the other one because it would be convergent. In that sense, yeah. So in this sense, yeah. Well, I know it's not an ideal answer. I know that, yeah. So so the best way to think of this would be to focus on pi of x. And think of this Lie x as the first term of an expansion. So the question is, the answer to your question, I think, should be like something like this. Well, yeah, pi of x is equal to that. But what are the other terms? You see, let me. No, that's a good question. Let's expand on that a little bit, and then we'll take a break, and then we'll finish. So can I erase this then? Okay, so your question, you see, imagine there is some unknown quantity like maybe f of x. So you have count something and something like f of x, and you say f of x is equal to x3, asymptotically to x3, as x goes to infinity. Then okay, that's good, but someone else, next person, another mathematician who is perhaps smarter or who has more tools or taken a longer time, proves that actually this is equal to x3 plus x2. Well, this is much better than that because it means really there is some extra term and the correction term is this. And then there is some other mathematician comes and says that this is x3 plus x2 plus log x. And then you go on x3 plus x2 plus log x plus e to the minus x log x, and so on. You see, these are hierarchy of information about the same function that at first revealed itself to us in this form, x cubed. But then now we're saying, no, there's more, and there's more, and there's more. Okay, so this is an example. Now let's look at pi of x. For pi of x, actually, which is, I said, okay, Li of x, or yeah, x over, yeah, so Li of x. In reality, pi of x has infinite number of terms. And there's a formula. It's called Euler, it's called Riemann's explicit formula. Riemann found all those terms. There are infinite number of terms. All those terms were found by Riemann. So this gives you the almost perfect information on primes, if you want. Yeah, yeah. For Riemann, actually, this was equality then. Even much better than asymptotic, and there are yeah. So this is called Riemann's explicit formula. I think I hope I can get to that. Yeah, I can explain that. But we have to develop some tools. Yeah. Yes. Yes. Yeah. Yeah. Pi of x is the real deal. Yeah, it's the real thing we want to understand. This is something. Yeah, that's the. Yeah. Okay, I think it's a good idea to take a break now, and then when we come back, I'll start with Dirichlet's breakthrough. So maybe we just, are there any questions? I can do a pause now, but where is the pause? Oh, there's pause here. This is the one, yeah, pause. Okay, so I should, okay, so this is recording now, good. So now let's go back to primes in arithmetic progression. Okay, now, so we want to show that we have the sequence a plus nb, and from 0 to infinity, and a and b equal to. Now, what happens in this case is that for some special pairs, a and b, you can prove this theorem that there are infinite number of primes by using Euclid's method. So elementary Euclid slide proofs exist just for a few pairs a and b. Now I don't know right now exactly which pairs you can use these elementary techniques to prove the theorem, but I know such pairs exist. A few pairs. There are not that many, or there. I mean, it's a small set anyhow. There's a and b. But in general, what you want to do, Euler's idea was in general to use these something like zeta functions to prove this. So Euler wanted to repeat his success with these sort of numbers. In general, Euler introduced generalizations of zeta function So these generalizations are now called Dirichlet L series. Although mostly they were introduced by Euler, called Dirichlet L series. I mean, Euler did not do it in general. Euler was, again, he was working with real characters only, so he was very special cases. He did not use complex numbers, and that was the things that was missing. Yeah, that's stopped him from proving the general theorem. But in some cases, he could prove this in general. So, so what are they? So let chi from n to c be a fully multiplicative function, i.e. chi of mn equal to chi m chi n. Chi of mn is equal to chi of m chi of n for all m and n, and chi of 1 equal to 1. I'm going to say a little more about this chi, but for now, that's enough for me. Then let L of, okay, so I have to remember, is it S and chi or chi and S? So my notation is L of S and chi. Yeah, S is the, is the variable, so should come for S of chi is equal to sum chi n over n to the s, and from 1 to infinity. This is called the Dirichlet L series. So, of course, there is a very special character. Can you tell me what is that? There's a very, very special distinguished character here I can use for chi. What is that? The identity character. Sometimes it's called trivial character. And it has a notation, it's called chi 0. So chi 0, n is equal to 1 for all n. Okay, so for this one, L of s chi 0 is nothing but sum 1 over n to the s, that's zeta of s, right? So this really extends Riemann's zeta function in this sense. For more general numerators, chi n over n to the s, and from 1 to infinity. That's one thing. Now, what happens, and in fact, okay, so there is an issue of convergence here. We have to worry about convergence, okay? So, so convergence issues, first of all. That's one issue that we have to address. But once you know that, then it's very easy. And again, this is one of your exercises, assignments. Then you can check that. There is an Euler product formula. In the sense that sum chi n over n to the s, and from 1 to infinity, again, is product of 1 minus chi p over p to the s minus 1 over p. So this extends the Euler product formula to all multiplicative functions like this. We have this. Now, the proof of this exactly is similar to, I mean, it's exactly the same as proof of Euler product formula for zeta functions. So proof is completely similar. To zeta s case. So now, this is not enough to prove the infinitude of primes in general for us. We have to still choose some very particular chi, which is called Dirichlet characters. And I will introduce those Dirichlet characters. So what then Dirichlet proved is the following. So this is what we are going to see soon. So Dirichlet showed that, and we'll see why that's the case, that if L of S and chi at S equal to 1 is different from 0 for any non-trivial, for all, I should say, non-trivial characters, then it follows that there exists infinite number of primes in arithmetic progression, and that was, so the theorem is proved. Then there exists infinitely many primes in the set A plus and B, and from 0 to infinity. You see, so we have now to do two things. First of all, we have to introduce the right kind of characters here, chi functions. They're called Dirichlet characters. And then we have to see why this statement of Dirichlet is true. It's not very difficult. We'll see that, although there's some nice idea involved. But then the most difficult part of the proof is to show that, in fact, L of S and chi is different from 0 at S equal to 1 for non-trivial characters. Of course, for trivial character, this is just infinite, because this is the zeta function at 1. And we know that that's infinite. So this is not what we want. We want to prove that for non-trivial characters, the value is finite. That's what we need. Okay, so there are now 3 steps in Dirichlet's argument. First, he has to choose the right kind of chi's. Then, by some manipulation, he arrived at this statement, and then he had to prove that actually this statement is correct. To prove this, he had to use some connection to algebraic number theory. He had to show that actually this is, so the proof that he had was to show that this is equal to the class number of some number fields. And that was a very roundabout, very difficult proof, because that theorem about it's called class number formula is a very, very deep theorem. And then people later on found independent proofs of this fact. Later on, they proved it. And that's what we use. That's the technique. We won't go through the original Dirichlet route, which, as I said, uses a class number formula for number field, which is much more important. All right. Okay, any questions? Yeah. Oh, A and B are used in the definition of chi. Yeah. So you tailor chi depending on A and B. Actually, B is what matters is really B. Yeah, that's a good point. Yeah. Yeah. For all non-trivial characters, then, yeah. No, I mean, we have to prove it for all chi's, because in the proof, all chi's enter. Chi trivial is a particular thing, is a distinguished element. We know what the value of the thing is infinite. That's Riemann zeta function at 1. But for other things, you have to show that it's finite. Yeah. Right. You'll see that why this is needed. Okay. So now let's look at Dirichlet characters, and actually I'm going to take a little bit of detour to introduce some general ideas about characters. That's very useful, no matter what. This is used in number theory, representation theory, beginning of representation theory, and a lot of things. So that's good to know that. So this is called abelian characters. The definition, let G be a finite abelian group a character on G is a group homomorphism chi from G to C star, which is C minus 0. So this is the multiplicative group of complex numbers. Multiplicative group of complex numbers. Okay? So what does this mean? And then it means that, so first of all, I'm writing multiplicative notation. So let me add it written multiplicatively. That's important to work multiplicatively. So basically, well, I mean, I just say chi of mn equal to chi m phi n for all m and n belonging to G. Of course, it follows that chi of 1 is equal to 1. That's true. If you want to use multiplicative additive notation, you would say chi of m plus n equal to chi m phi n. If you want to use additive notation, that's both are, you can use both, right? So listen. All right. So now, of course, trivial character, as I said, is always there. Phi 0 is identically equal to 1. That's always, we always have the trivial character. Okay, now let's look at some examples. The integers modulo n. Maybe I'll just use, I mean, bz. B bigger than or equal to 2 integers modulo e. So this is the basically cyclic group of order B, right? This is just additive group, cyclic group of order B. So let's look at the characters of this. So now what we can do, we can choose, let omega belong to mu E. Now, what is mu B? Mu B is the group of beat roots of unity, okay? So is the set of all Z belonging, oops, sorry, complex numbers such that Z to the power B equal to 1. Obviously, this is a group of order B with under multiplication. So this is a group of order B under multiplication. So let's pick a beat root of unity, and then let pi omega from Z over BZ to C star, define it like this, pi omega of some number like n mod B, let us be omega to the power n. We just raise to power n. And this is obviously a character. Okay, so chi omega is a character. And in fact, it's easy to see that all characters are of this form. And all characters of the cyclic group are of this form. I mean, the reason for this is that if you have a character, it's going to send the generator to an element whose beat power is going to be 1, because in the domain, the beat power is 1. So it has to go to an element whose beat power is 1, and so it has to be in this mu b. And then for all other elements, we can just... So all you have to do, you have to know where the generator, like 1, goes to. Generator of cyclic group is 1 mod b, right? And 1 goes to omega. Pick any omega you want. And okay, so yeah. No primitive is needed. We have this. Yeah, exactly. So we have this. So there is a notation that's called the dual group. G hat. Again, I'm assuming G is a finite abelian group. Okay, so G hat, the dual group of G is by definition the set of all characters of G. Chi is a character. So the dual group is the group of all, is the set of all characters on the group. Now, if you have 2 characters, you can multiply them, right? On the multiplication, this is closed. Chi1 times chi2 of G, by definition, equal to chi1G, chi2 of G. So this G hat, in other words, it shows that G hat is a group. Is again an abelian group. And what this first example here shows is that what is we calculated the dual of the cyclic group of order n. What is that group? The dual of cyclic group of order n. Yes. Again, we just showed that it's a cyclic group of order n. So it's isomorphic to itself. That's very, so G hat, in fact, Z over BZ hat is isomorphic to mu B. So these are 2 different incarnations of the same group. Here, it appears multiplicatively as the beat roots of unity, here as integers modulo B. But that's, there are different incarnations of the same object. This is isomorphism of groups. And so now, just a curiosity, you can actually prove that the dual of any finite abelian group is isomorphic to that group. So let me just write this statement, because this is something useful in general to know. Maybe we will use it, I'm not sure, but let me write it anyhow because we are there. So theorem for any finite abelian group G, we have G is isomorphic to G hat. So this is isomorphism of group. Yes. No, that's a good point. There is no canonical isomorphism, unfortunately. The isomorphism I'm going to choose depends on choice of basis. So it's a kind of dirty isomorphism. It's not canonical. And yeah, this is, in fact, a deep point that there is no canonical isomorphism. Yeah. You have to choose some decompositions. Yeah. So exactly. So let me just do the proof. Well, we use the structure theorem of finite abelian group. Any finite abelian group can be written as products of cyclic groups, right? So write G as isomorphic to Z over B1Z cross Z over B2Z cross Z over BLZ. You can always do that. That's a beautiful theorem from group theory, elementary group theory. Okay? Now, there is an exercise you will do that G cross H dual is isomorphic to GH cross G dual cross G dual. So if you take product of two groups, the dual of the product is product of the duals. That's very nice. So once you prove that, then you, which is in your assignment, then you will show that you have shown that G hat is isomorphic to Z over B1Z hat cross Z over BLZ hat, but each of them is isomorphic to itself by this exercise we did, right? So this is Z over B1Z cross Z over BLZ. Okay, so but this isomorphism is not canonical. It's not functorial. You think about it, and then you'll see why this is not functorial. All right, so one thing that we need of this is orthogonality relation. So let me write it down. Any questions, by the way? So the Pontryagin duality, I can do that. Yeah, yeah. I will write it down. Yeah, that's so. Is that what you meant? Yeah. The second dual is always isomorphic to G, but that's canonical actually. So that's pretty good. Yeah. So I'll write it now. So let me. But before the because yeah. So this is, let's call it first orthogonality relations. So this is for any character chi belonging to G hat, we have sum of chi of G, G belonging to G is equal to, you see, we are summing the values of different characters on fixed element, same character on different elements of the group. So we are kind of averaging over this, right? Now I'm saying this is equal to, first of all, is equal to order of G if chi is chi 0, is the trivial character, and is 0 for otherwise. Otherwise. So this is the famous orthogonality relation. You will see this sort of orthogonality relations for all groups, compact Lie groups, and that's a hallmark of representation theory. But they appeared first in mathematics in papers of Gauss and Dirichlet in this context. So proof. Okay, so obviously the first statement is obvious. I mean, if G is equal to, so first claim is obvious. So nothing to prove. So now let's assume that chi is different from chi 0. It's not trivial. So what does that mean, that chi is not the trivial character? It means that there is an element such that there's an element H such that chi of H is not 1. Because if it was a trivial character, it would be 1 everywhere. So hence, I just say there exists H belonging to G such that chi of H is different from 1. Okay. Now I'm going to write this sum chi of G belonging to G. Now I use the group property. I just write it as sum chi of GH, again G belonging to G. You see, as you move G and this GH covers the same elements. This is the trick in group theory. Always go there. So it's a symmetry. Now we are using the symmetry inside the group heavily, right? So these two sums are the same. Now I can use the multiplicative property of characters to write it as chi G, chi H, right? Again over G. But now, so I can factorize chi H. So I just say this is chi H times sigma chi G, G belonging to G. So what did we prove? We proved that sum that we want is equal to the same sum times chi of H. So let's take note of that. So we just proved that 1 minus chi H times sum that we want, chi G, over G is equal to 0. So you just bring this to the left-hand side and you get that equal to 0, right? Okay, now this is different from 0 because I just chose H such that chi of H is not 1. Okay, so this is better with 0. Sum chi G equal to 0. Okay, so that's the first orthogonality relation. That's going to give us huge dividends, and it's very, very important in general in representation theory. Oh, it just the orthogonality relation. This shows that yeah, there is a way to introduce inner product on the set of all functions on G, and it just shows that different characters are actually orthogonal to each other. Well, they are orthogonal, yeah, they are not orthonormal because this is not equal to 1, this is G. But you can normalize it to turn. So it means that basically characters form a very special basis for class functions, not for everything, but just for class functions. Yeah, so this in representation theory becomes important, yeah. I'm not sure I can give more kind of clear answer than this. All right, now I called it first orthogonality relation. Is there a second orthogonality relation? What, sorry? No. That would be dual, which is what we do. What should I do then? In this time, yeah, we just sum over all characters over a fixed element this time. So this is called second orthogonality relation. Let's prove that also. Question? Is that clear? Okay, so let me write the second orthogonality relation. Second orthogonality relation is that sum over all characters. So this says for any G belonging to G, sum of all characters, phi belonging to G hat, phi of G is equal to, again, is order of G if G is equal to E, the identity of the group, and is equal to 0 if G different from E. So the proof of this needs a little more thinking. It's not totally depends on that algebraic trick that I used. So what I need in this case is, okay, of course, first case is obvious again. First claim is obvious. So we have to show that for any G different from E, so need to know that for any G different from E, there exists a character on capital G such that chi of G is different from 1. There exists character chi belonging to G such that chi of G is different from 1. You see, this is a dual statement of the things that we chose here. Now, that's not obvious because you cannot just say, hey, there is a character, because there's some conditions you have to satisfy. It's not obvious at all. But I will tell you how to prove that, but let's assume this. Assume it. Then what we can do, well, I can just, because just write epsilon be such character. So is a character such that epsilon of G is fixed, is different from 1. Then we can just write sum chi G over G, no, over chi, again sum I epsilon chi over G over chi. Again, now I'm using the group property of the dual group here, the characters, because just multiply, okay? So we get that. So now this is equal to sum epsilon G chi G over chi, and then the rest is the same. I don't write it. That's exactly the same idea. Now, proof of existence of this element, there's an exercise, but that's not difficult. It's one of your assignments. You will show that. So for any H subset of G subgroup, and for any character chi, a character, you can always extend this character to G. An extension by tilde of chi to G. That's always possible. So this extension theorem reminds you of what result in analysis. Actually, those who have taken functional analysis. Harmonic theorem. Harmonic theorem says that if you have a subspace, a linear functional, basically you can extend that linear functional from that subspace to the whole thing in such a way that norm of the linear functional does not increase, and so there are some continuity issues, but that's exactly on the same footing, right? Same level. All right, so you prove this, that's not difficult. Then in this case, you have to take H to be the subgroup generated by G, by that element G, and you already know how to write a character which takes a non-unit number on this G, because we know all the characters of the cyclic group. That would be a cyclic group generated by G, and then you go on from there. Is that clear? Okay, so now tomorrow, so we have to start with Dirichlet characters. So this is a general basic theory of abelian characters or characters of finite abelian groups. But as I said, this is not enough. We need some particular type of characters called Dirichlet characters. They were introduced by Euler for real valued such things, and for Dirichlet in general for complex value things. And then we move towards the proof of the theorem. Okay, so let me just stop now. I don't know how to stop. Oh yeah, I can stop now. Okay.